Okay, you can see in the problem here that we've got a cliff and a projectile is being fired with an initial velocity directed 17 degrees below the horizontal. This thing will follow a parabolic path and end up with some final velocity the instant before it hits the ground. It'll travel some distance, delta x, from the base of the cliff, and it'll be in free fall with an acceleration of 9.8 meters per second squared directed downward. Now our sign conventions for this problem will be generally in the direction of motion, so I'll make to the right positive and I'll make down positive. Now for our initial velocity, we're going to need to split that into components, so let me draw a little coordinate axis here. So here's our V0 making an angle of 17 degrees below the horizontal. I'm going to split that into V0x, which is V0's cosine 17, V0y, which is V0 sine 17. Note that both are positive because of my sign conventions here and here. Alright, so our first goal is to solve for the delta x, so I'm going to write down what I know for my two components. Now, by this time it should go without saying that you should be doing this one yourself. So if you haven't already filled out a table of x and y, what we know and what we don't know before we begin the problem, you should do that. And you should go ahead and finish the problem, do as much as you can. So, alright, for delta x, we don't know that. V0 x, we've calculated up here as V0 cosine 17. So that's, let's see, V0 x is 33 cosine 17, and it's positive. So that works out to be 31.56. The x acceleration is 0, right? The y acceleration is 9.8 meters per second squared, right? Because it's in free fall, so I've taken my acceleration vector here, which remember is 9.8 meters per second squared directed downward. Since it's directed downward, it has an x component of 0, and it has a y component, and the y component is 9.8 meters per second squared, and it's positive because it's directed downward. Alright, and since the x acceleration is 0, I can also say that the final velocity in the x direction is 31.56 meters per second, and we've been given that the time is 2.8 seconds. Looking over at the y, we don't know delta y, how far it falls. We know V0 y from up here is 33 sine 17, which is 9.65 meters per second. Again, that's positive because we've made down positive. Vy is not known. It's the final velocity the instant before it hits the ground, and time of flight is 2.8 seconds. Alright, so let's do part A. Part A says delta x is equal to V0 xt plus 1/2 at squared, which is 31.56 times 2.8 plus, the second half of that 0 because the acceleration is 0, so that works out to be 88 meters. Okay, so there's part A. Part B, I'll go ahead and put that answer there, 88 meters. Right, part B, we need to find the final velocity. Right, what we need to do is we need to find the x and y components of the final velocity, so we need to find that Vy. So I'll use the equation that doesn't have delta y in it. That's Vy is equal to V0 y plus a t. It's going to be 9.65 plus 9.8 times 2.8, which is 37.1 meters per second. Okay, so Now I've got the components of my final velocity. I need to make a little triangle that tells me how to find Vy. So my triangle is going to have an x component Vx, which is 31.56, Vy, which is 37.1, and the resultant vector V that's going to make some angle theta below the positive x-axis. So the magnitude of V can be found with Pythagorean theorem. Okay, if I plug in 31.56 and 37.1, I get 48.7, which I'm going to round to 49 meters per second. Looking at the problem statement, I'm giving two significant figures throughout. And then to find the angle theta, theta is the inverse tangent of opposite over adjacent. That's the y component over the x component, so that's 37.1 over 31.56. So my calculator tells me that's 49.6 degrees, which I'm going to round to 50 degrees below plus x. Right, my calculator gives me the 50 degrees. My common sense gives me the below plus x. So I've got the magnitude and direction of the final velocity, and I'm done.